Hi everybody, we're going to go over chapter 14 in your radiation protection book. Okay, first of all, you are going to get increased exposure in general fluoroscopy, IR, that employ high-level control fluoroscopy, mobile examination, so mobile x-rays, portables, and C-arm. So we're going to learn how to do everything possible to protect you and the other medical imaging professionals. Okay, we already talked about the patients in a previous chapter. Now we're talking about how to keep you and your coworkers and the RADs that you work with and the other physicians that you work with and nurses safe around radiation. So first we're going to talk again about the effective dose limits. The NCRP recommendation for the annual occupational effective dose for any occupational worker in radiation is 50 millisieverts. That's a whole body exposure. It does not include any medical procedure that you yourself receive, okay, and it does not include the background radiation. So this is the high range dose limit, okay? 50 millisieverts per annum. You need to remember that. Okay, it does not include personal medical exposure, does not include natural background exposure. The lifetime effective dose in millisieverts should not exceed 10 times the person's age in years. Okay, now that's two different things. So you have an effective dose limit that's recommended by the NCRP, that says your annual occupational limit effective dose should not be any more than 50 millisieverts. Okay, and then there's a second guideline that says also your lifetime dose should not exceed 10 times your age. Okay, so I want to put this in perspective. Let's say that you're 20 years old and you just got your x-ray license and you are working and 25 years goes by. Okay, you're now 45 years old. You have been recommended by the NCRP to not receive any more than 50 millisieverts every single year. Okay, that is the top limit. You shouldn't get anywhere near there, but say you're in IR and you get a lot of fluoro exposure. 25 years of occupational exposure times 50 millisieverts each year adds up to 1,250 millisieverts. That would be the limit that you would acquire at the high range. Now remember, this is the high range, okay, and nobody should get near that according to their guidelines. But you could have a limit of 1,250 millisieverts. Okay, that's working for 25 years. Now look at the lifetime effective dose in millisieverts, which should not exceed 10 times your age. So if you started working at 20 and you've been working 25 years, your time, you're 45 years old right now, your time in your career is 25 years, so your age is 45 years. You times that by 10, your maximum lifetime effective dose should not exceed 450 millisieverts. Now we just calculated the one saying you've worked 25 years in the field and at 50 millisieverts every year you could get up to 1,250. No, you have to take that the more conservative of the two. So even though the top guideline is 50 millisieverts per year, you should not get anywhere near there. Okay, your lifetime effective dose that you need to keep in mind is 10 times the person's age in years. Okay, so just keep that in the back of your mind. You're going to need to know that. Okay, so once again, the annual occupational effective dose limit, 50 millisieverts. Now that's for occupational people that are in the radiological field. Non-occupational effective dose limits are another thing altogether. Okay? The annual limit for members of the general population, which does not include us, is only 1 millisievert for continuous or frequent exposure from artificial sources. Okay? That's other than medical procedures or natural background radiation. So you can think of other sources of radiation. So say one of those nuclear accidents we just talked about, your annual limit for the general population is set at 1. That's what the recommendation is. Now, the limitation of exposure of the general public is based on a reasonable level of risk. And we talked about that in a previous chapter as well, where they took other occupations that have a very minimal risk, and they're comparing our field with that, and they're holding the standard to keep everyone safe. Now, the allowance, the big disparity there of 50 millisieverts for occupational radiation workers compared to the general population that is only 1, okay? And that's for frequent exposures. The general reasoning behind that is that the workforce in radiation-related jobs is very small when we're compared to the population as a whole. So that amount of radiation that is received by us can be larger than the amount that the entire general public would receive without significantly altering the genetic dose. Okay? I hope that makes sense. Although the radiographer and other diagnostic imaging personnel are allowed to absorb more radiation, the equivalent dose received must be minimized whenever possible, and that just makes sense. You're going to always err on the side of safety to prevent somatic, which remember what that means. It's the Latin word for body, and genetic damage. The best way for you to do this is the ALARA concept, okay? Whenever applicable, you have to apply the principles of time, distance, and shielding. You always collimate the beam, always, always, always. And you're diligent about collimating it to the field of view. Only necessary primary beam should hit that IR. And because of continual use of such radiation protection awareness procedures, this ensures a high degree of safety for most radiation exposure. Radiography is not considered a hazardous profession if those guidelines are utilized. And this is just showing an example of using proper collimation to the area of clinical interest, only hitting the image receptor. You're also going to avoid repeat imaging, which eliminates additional exposure to your coworkers and yourself. The patient is the primary source of our radiation that we receive. The patient is the source of scattered radiation. So during a diagnostic examination, the patient becomes the source of scattered radiation, and that is due to Compton interaction. And the safest place is at a 90-degree angle to the primary X-ray beam at a distance of 1 meter, okay? That's been measured to be only 1/1000th of the intensity of the primary X-ray beam. And we'll learn later that other places that you can stand in the room are not nearly as safe. The 90-degree angle is the safest spot, well, in the room. If you can get behind in the control area, that's where you need to be. Okay, scattered radiation is an occupational hazard that we have. It poses the greatest hazard in our line of work, and use of any device or appropriate technique that lessens the amount of scatter radiation will significantly reduce your occupational exposure. Okay, and this is just showing how we can reduce our exposure. Besides filtration of our X-ray beam, okay, we also can use protective apparel. So they're showing you 2 types of protection. One is the lead apron, the other one is the lead barrier. It's an acrylic lead barrier. Okay, filtration of the X-ray beam removes non-useful low-energy photons from the primary beam. Since there's less number of photons entering the patient, there will be less scatter radiation. So that will benefit you as radiation workers as well. Without proper filtration, more of those non-useful low-energy photons will interact with the patient's body, which increases scatter and could cause possibly an increase in your equivalent dose. Okay, again, protective apparel, lead aprons, shielded barriers, the curtain on fluoro machines protect you from secondary radiation, which is what we are concerned with. Okay, we should never be in the primary beam, so that should not be a concern for us. The concern that we have is the secondary, which is scatter and leakage radiation. The lead aprons can protect you from that. They are available in thicknesses such as 0.25 millimeter lead thickness, or lead equivalent, you will see on the tag, 0.5 lead equivalent, and 1. There's also in between. However, there's some guidelines that the NCRP has put out and recommendations have been made that California enforces. The higher lead equivalency, of course, provides greater protection from the radiation, but the garment will weigh more. The wraparound style apron is the best protection because that way you don't have to worry about turning around while, if you're in the room, while a procedure is in progress. But lead aprons do require special care to prevent them being damaged. Okay, here is a table that shows you the weight difference, and I calculated one of them out. So say you had a 1 millimeter lead equivalent thick apron because you wanted to be the safest you could be. Look here on this table at 100 kVp procedure. That 1 millimeter lead equivalent apron blocks 94% of the radiation. Okay, it attenuates 94% of it, which would be what we would want to err on the side of caution. We'd want to wear that whenever possible. However, the weight of that apron is 5 to 12 kilograms. And I know this isn't in pounds, so I converted 12 kilograms, saying we take the heaviest one. That weighs 26.5 pounds. So if you think about it, you have to wear that apron for multiple procedures or a lengthy procedure, that's really going to strain your body. It's going to strain your back. So the best apron, the most versatile apron out there is the 0.5 millimeter lead equivalent because it weighs significantly less. It still blocks 75% or attenuates 75% of the radiation, and it weighs a lot less, okay? It can weigh half of what we had before, which would be about 13 pounds, okay? So just something for you to think about. Keep in mind that different sites have different thickness aprons, okay? And you need to be conscious of which one you're wearing. So don't just grab an apron. Whenever you have some downtime, look at the aprons and see which thicknesses you have. If you have any different thicknesses, try to remember which ones are which. Okay, another way you can reduce scatter is technical exposure factors. So this influences the quantity of the radiation produced, okay, which influences how much is going to reach you by scatter after it exits the patient. If you use a higher kVp, it increases the mean energy of the photons in the beam, thereby decreasing the amount of scatter radiation coming off the patient, okay? If you increase your higher kVp, you're going to lower your mass to compensate, and that decreases your photon beam intensity. As average energy of the beam increases, the percentage of radiation that is forward scattered increases. Therefore, less side scattered radiation is available to strike imaging personnel, and your equivalent dose will be reduced. You also want to try to use high-speed image receptor systems. Okay, that affects your technique as well. And you can require smaller radiographic exposures, which is less MA. Fewer photons are available to produce Compton scatter, etc., also decreasing your equivalent dose. Okay, also keep in mind, if you have to repeat images, that increases your dose because now you're increasing the patient's dose, which increases scatter, which can come back and hit you. So repeats by mispositioning need to be at a minimal, okay, because they cause additional radiation exposure for both the patient and the technologist. Okay, dose reduction methods and retakes continued to decrease your scatter radiation exposure. Patient restraint, that's going to prevent repeats because there's no motion. And we don't restrain patients, as we know, but if it were to be necessary, we can definitely utilize family members, friends, people like that. So if someone needs to help hold someone up, it should never be a technologist. It should never be a student. It should be a friend or a family member. Okay, radiographers should never stand in the primary beam to restrain a patient during a radiographic exposure. Mechanical restraining devices, whenever possible, should be utilized, such as the pigostat. Okay, if other kind of restraint needs to be utilized, you would have to enlist the help of a physician or the patient's nurse. We do not get to restrain patients other than pigostat or imaging devices that have been approved. If restraint by people is necessary, you're going to select a friend or family member. And a pregnant woman should never be permitted to assist in holding a patient during an exposure. So if a pregnant woman comes in with a child that needs a chest x-ray, and the pigostat cannot be utilized for some reason, but that child needs to be held or helped out, the pregnant mother cannot hold that patient. The technologist cannot hold that patient, or a different technologist, I should say, and a student should never hold the patient. We're going to need to call another friend or family member to come and assist. Okay, patient restraint. So this is just an example of a person helping out. They have a friend or family member can have the lead apron on, give them gloves if they need gloves, give them thyroid shield if they need thyroid shield. If they're going to be in the room with their friend or family member while you are taking a radiograph, feel free to get them all leaded up, show them where they should stand and how they should hold that patient, but it should never be a radiographer. It should be just friend or family. Imaging department protocol for pregnant personnel. They should be able to continue performing their duties without interruption of employment if they follow established radiation safety practices. Policies for protecting pregnant personnel from radiation are in force. You can voluntarily declare your pregnancy. If you do so, the health facility will recognize the pregnancy. They will give you extra counseling, and they will make sure that they order a second radiation badge. It's a fetal monitoring badge that you will wear on your abdomen that will monitor radiation exposure to that area. Okay, so if that were to occur, the facility through your radiation safety officer will give you counseling. They'll give you that additional monitor to be worn. If you needed to wear a protective lead apron, the additional monitor will be worn underneath that lead apron because this is fetal monitoring, not you as the radiographer, okay? The purpose of this is to ensure that the monthly equivalent dose to the fetus does not exceed 0.5 millisieverts. That's a monthly dose, not an annual dose. So monthly cannot exceed 0.5 millisieverts. You need to remember that. The limit for the entire pregnancy, all 9 months, is 5 millisieverts. The equivalent dose limit is designed to significantly restrict the total lifetime risks that are associated with radiation in the fetal stage, the risk of leukemia and other malignancies that you can remember that we had back in previous chapters. Okay, protection for pregnant personnel. So say you have declared your pregnancy, they cannot just fire you and tell you to come back in 9-10 months, okay? You're going to acknowledge your counseling and the understanding for the radiation safety measures. You are going to probably have to read and sign a form acknowledging that you have been counseled, because that is required for the radiation safety officer to perform that service and to document it as per their safety policy. And the dosimeter companies will provide that separate monthly report that tracks just the exposure for the fetus. Okay, there's protective maternity apparel that can be available. There is an apron that is a 0.5 millimeter lead equivalent, but it also has an extra 1 millimeter lead panel that goes just over the abdomen there. There's also pregnancy aprons that have additional material in the front that can be worn comfortably so that it still fits around the shoulder and around the waist, but you just have that extra protection in front of you. The wraparound protective apron should be 0.5 millimeter lead equivalent as well. Work schedule alterations. In accordance with ALERA, work schedules are designed to distribute radiation exposure risk evenly to all employees. So just because you're pregnant does not take you out of the rotation for fluoro or portables or OR. If that did occur at your site, then you would be increasing the exposure to all of the non-pregnant personnel, and that is not fair, nor is it necessary. So all you need to do, a pregnant radiographer does not need to be reassigned to a lower radiation exposure. All you need to do is use your safety precautions just like you normally would, and everyone is rotated the same way. So you're just going to monitor the fetal dose to make sure it does not exceed that risk. And your RSO will be the one in charge of all of that. Okay, the basic principles of radiation protection for personnel: exposure reduction. Okay, occupational radiation exposure of imaging personnel can be minimized, of course, by time, distance, shielding. The time, decreasing the length of time spent in the room. So if you decrease the length of the time that you spend in the X-ray room doing procedures, then there you go. You've decreased your exposure. Distance, stand away at the greatest distance possible from the energized beam. Shielding, interposing a radiation absorbent shielding material between the worker and the source is another way. So time, distance, and shielding, that's the cardinal rule. So just to get a little bit more into the time, the amount of radiation a worker receives is directly proportional to the length of time that you are near the path of ionizing radiation. Most fluoro X-ray equipment have a 5-minute timer to alert the radiologist or other equipment operator. Radiographers should be present in the fluoro room only when needed to perform a relevant patient care or duty associated with the procedure. Otherwise, stand back behind a protective barrier, behind the radiologist, wherever you need to be. Distance, the most effective means of protection from ionizing radiation. As you will know, it's the inverse square law. Okay, imaging personnel receive significantly less radiation exposure by standing farther away from a radiation source. So this leads us into the application of the inverse square law. So the inverse square law expresses the relationship between distance and intensity. The intensity meaning the quantity of radiation. It governs the dose received. So the law is the intensity of radiation is inversely proportional to the square of the distance from the source. And this just illustrates that point. And it shows you that this primary beam, when it hits this first barrier right here, okay, so say this orange square, this is the primary beam at 1 meter. Okay, if you increase the distance, now the same amount of energy that was just focused on this right here is now focused all across this, okay? So the intensity is just decreased. Alrighty? So more distance equals less intensity, less quantity of radiation. If you double the distance, 1/4 of the intensity. 3 times, 1/9 the intensity, and 4 times, 1/16. Okay, the inverse square law formula is stated as such. I1 over I2 equal to D2 squared over D1 squared. So there is an example here. If the radiographer stands 2 meters away from an X-ray source instead of 6, the difference between 2 and 6 is 3 times. That's going to decrease your exposure by a factor of 9. Okay, second principle from time distance shielding. Here we go. Third principle. Shielding. Use it when it is not possible to use time or distance. Okay, protective shielding needs to be of the appropriate thickness. Lead and concrete are the most common materials used. And since we can't shield ourselves with a concrete apron, that's where we're getting our lead. Concrete is in our materials for our actual rooms. The accessory devices, such as aprons, gloves, protective eyeglasses, thyroid shields, are all made of lead impregnated vinyl or acrylic. The effectiveness of the shielding material depends on the atomic number, the density, and the thickness. Okay, shielding continued. So protective structural shielding. This is where we get into structural barriers, such as your walls and your doors in an X-ray room. They have all been designed to provide radiation shielding for the department and the general public. It ensures that occupational and non-occupational effective dose limits are not exceeded. And this is done by calculations that a qualified medical physicist determines. Okay, there's 2 different types of shielding. There's primary and secondary. For the primary protective barrier, this is the barrier that the direct beam is hitting. And the purpose is to prevent that direct or unscattered radiation beam from reaching personnel or the general public on the other side. So, for instance, the wall behind the wall bucky. Okay, so that's a primary barrier. The location, it's going to be perpendicular to the undeflected line of travel of the X-ray beam. So the X-ray beam is perpendicular to this main protective barrier. The specifications for a 120 kVp X-ray beam, so it's going to be the most or the highest kVp that tube is capable of. That's what the barrier has to be designed to prevent it going through that barrier. So for a 120 kVp X-ray beam, that wall needs to have 1.6 millimeters of lead in it. It's got to extend 2.1 meters from the floor of the X-ray room when the X-ray tube is 1.5 to 2.1 meters from the wall in question. So all of these distances and measurements are taken into account when they build imaging suites. And this is a good picture. Okay, this is our X-ray tube. This is our primary beam. This is our wall bucky. And this is your primary barrier, because this is the wall that's perpendicular to that primary beam right here. It has to be thick enough to attenuate any of those primary photons coming through that wall to keep any personnel or non-occupational personnel safe on the other side of this wall. So the minimum for 120 kVp stream or energy beam is 1.6 millimeters of lead. The other walls that are not perpendicular to the point of the primary beam, these are called secondary barriers, and we'll go over that as well. Okay, the secondary protective barrier, this purpose is to protect against secondary radiation. And remember, secondary radiation is anything other than primary. And secondary includes leakage and scatter radiation. And that location of the secondary barrier is any wall or barrier that is never struck by the primary X-ray beam. So that is classified as a secondary. So that could be every other wall, every door, every window that is in that X-ray room. All of those other surfaces are secondary barriers. And the secondary barrier should overlap the primary one by approximately 1/2 inch, and they do inside the drywall. And the specifications for those at 120 kVp are 0.8 millimeters of lead. So that's half of what the primary needs to be. Also, for secondary protective barriers, personnel must remain completely behind the barrier. The observation window in the barrier will typically consist of 1.5 millimeter lead equivalent. Now, is that because the primary beam is going to be pointed at the window? No. Exposure of the radiographer will not exceed a maximum allowance of 1 millisievert per week. So in a well-designed facility, the exposure should not exceed even 0.02. So 1 millisievert per week in that control area back there is going to be very high range, the highest level of the range. Okay, the exposure cord must be short enough that the exposure switch can be operated only when the radiographer is completely behind the control booth barrier. Okay, so we have a wall that's a secondary barrier that the radiographer stands behind to initiate the exposure. The reason why that we need to stay behind that wall while that exposure is being done is because of the scatter radiation that is bouncing around inside that room. Okay, the control booth barrier continued. It's to protect the radiographer from that secondary radiation, leakage, and scatter. It is located in the X-ray rooms housing permanent or non-portable radiographic equipment, which makes sense. You don't have a control area if you don't have a permanent tube installed. Okay, the specifications for just the control booth barrier, it must extend 2.1 meters upward from the floor. It must be permanently secured to the floor. So that means you cannot have a rolling shield just in front of you in a control area. You must have a permanently designed, secured to the floor barrier wall. Diagnostic X-rays should scatter a minimum of 2 times before reaching any area behind this border. And you need to know this. This is a test question. So those X-rays should scatter a minimum of 2 times before it ever reaches that secondary barrier that you are behind. Okay? And this is just some pictures. So this is your control area. This would be a secondary barrier. This is a secondary barrier with an impregnated lead window. Okay? And remember, the lead needs to be impregnated. Approximately 30% lead needs to be in that acrylic window. Okay, this is a more modern facility that has a panoramic view to the imaging suite. And this is also an acrylic lead impregnated window that needs to have 30% lead in it to be appropriate shielding. It provides a panoramic view. It gives the patient a little bit of ease of mind. A lot of patients will say, "You're going to leave me." And this way you can say, "I can see you right through the window." Okay, another type of shielding that you can use is called an overhead protective barrier. These are usually mounted on the ceiling, And they're used for IR procedures, cardiac catheterizations, things like that. The radiologist can simply bring them down, or the assistant can bring them down in front of the radiologist. It protects them from scatter radiation. The shielding typically will offer 0.5 millimeter lead equivalency protection. Okay, another way to shield are accessory protective devices. So here is different patterns for lead aprons. Remember, the physical weight is a concern. To combat the weight of lead, they are starting to get garments impregnated with tin. I personally have not ever used a tin apron, so I don't know how much lighter they are, but if they can attenuate the photons, that is a great improvement. For 100 kVp beam intensity, the apron must be equivalent to at least 0.25 millimeter thickness of lead. Actually, this is what is required. Okay, 0.2 millimeter thickness of lead is required for routine procedures. 0.5 or 1 millimeter lead equivalent affords greater protection, so that is what is recommended. So 0.5 millimeter lead equivalent is the most widely recommended thickness in regular diagnostic imaging. Okay, here are the guidelines though for accessories. The gloves need to be a 0.25 millimeter lead equivalent. Okay, thyroid shields need to be a minimum of 0.5 millimeter lead equivalent. Protective eyeglasses I wear to reduce scatter radiation to the lens of the eye and prevent cataracts need to contain a minimal lead equivalent of 0.35. You need to remember these numbers. Okay, moving on to other safety concerns. Radiographers should avoid handling or severely bending the high tension cables that are connected to the positive and negative terminals of the X-ray tube. And we've all done this. We've all been in an X-ray room where we have spun the tube around to accommodate our patient, and you end up getting all of those cables wrapped around the mounting pole or mounting housing. You need to watch that, okay? You do not want to severely bend those high tension cables, and you never want to touch the tube housing or cables while an exposure is in progress. It should be impossible to do that if you are pressing the exposure button, but if you are in the room and someone thinks you're safe and you're touching one of these cables, the possibility of an electrical shock, let alone the leakage radiation that's close to you, is a concern. Okay, so we're going to go back to personal protection, but this is during fluoro procedures. So the guidelines are almost the same. There's a couple differences. First of all, you should stand as far away from the patient as is practical and move towards the patient during fluoro only when you are needed to do so. Okay, that is to ensure protection from scattered radiation which emanates from the patient while the fluoro is on. Protective aprons in fluoro have to be 0.5 millimeter lead equivalent. Remember, we had just said 0.25 was fine. That was for routine procedures. This is now fluoro. Fluoro, it is now 0.5, okay? Protective gloves are the same. It needs to be 0.25 lead equivalent, and you would be well versed to keep those lead aprons where you can find them. If you do need to hold a patient or hand them barium because they're laying flat while the radiologist is fluoroing, you would be well to have that hand in a lead apron. It won't do you any harm, and it is good for you. The thyroid shield needs to be 0.5 lead equivalent. And then, of course, you want to be wearing a wraparound style apron. That way you don't have to worry about keeping the front side towards the radiation source at all times. You can turn around if you have to. Dose reduction techniques that we can employ besides wearing protective gear that are going to save radiographers and other personnel from occupational exposure Some of these methods are adequate beam collimation. We always want to collimate. Even in fluoro, we're collimating. Adequate filtration. Okay, so this is usually inherent in your tube, but you can add it if needed. Control of your technical exposure factors, so keep an eye on what you're using for your KVP and writing your doses down if possible. Your skin, source to skin distance, you need to watch that. Use of a cumulative timing device. So this device should always be running when that fluoro unit is on so that you can note how much fluoro time has been with that patient. And the diagnostic type protective X-ray tube housing. Okay, now one of the things they talk about that is going to help protect you is called a remote control fluoro system. This provides imaging personnel with the best radiation protection. The system allows the radiologist and the assistants or radiographers to remain outside of the fluoro room at a control console, which is located behind a protective barrier until you are needed. Okay, now unfortunately, this doesn't get utilized a lot because we have made our practice of our fluoro exams being in the room with the patient, doing things as the fluoro is on. Okay, so you don't see remote control being utilized a lot. Since that is the case, you need to add distance and use the inverse square law. That's going to increase your protection in those rooms. However, the protective curtain on the fluoro machine, that needs to be utilized at all times with the exception of invasive procedures that utilize needles. In that case, the curtain can hit that needle and cause further harm or increase fluoro time with having to reposition. You never want to do that. So that in that case, the curtain would be removed if that's only at the direction of the radiologist. In all other exams, that protective curtain should be located on that fluoro device, on the image intensifier. It does have a minimum of 0.25 millimeter lead equivalent. Okay, remember that number. The Bucky slot shielding device. Now this is different than the curtain, you guys. And if you notice on your fluoro tables, you usually move the Bucky tray down to the foot of the table when you're using the X-ray tube or anything else on that table, when you're taking overheads, things like that. When you move that Bucky down to the foot of the table, there should be a device called a Bucky slot shielding device that automatically covers that slot opening, okay? It's imperative that this is in working condition because it protects the radiologist and anyone else in the room, the radiographers, go at the gonadal level. This equivalent should be 0.25 millimeter lead as well. And what this does is when you're fluoroing, it just takes this Bucky slot shielding device, covers that opening up and protects you and the radiologist and anyone else helping out in the room. And without this device and without the protective curtain in place, the exposure rate for the radiologist doing the fluoro would exceed 1 milligray per hour at a distance of 0.6 meters from that side of the X-ray table, so it makes a difference in your dose. Okay, rotational scheduling of personnel. This is a good idea. It's not something that you have a lot of control over right now, but when you become a supervisor, you can just keep this in mind that you need to rotate your personnel. And if you think that you are getting a high level of dose due to rotating through these high occupational exposure areas of radiology more than other people, when you become a staff member, that is definitely something that you can talk to supervision about. Okay, but normally you would rotate personnel through those high occupational exposure areas in radiology, such as fluoro, doing portables, special procedures in the IR suite, go into OR, things like that. So the time that you spend less time in these higher radiation tasks are going to decrease your exposure. So if there's a rotational pattern, it keeps everybody on the same level. okay, because there's less time spent doing the high ones. You're more in the department. Your exposure rate is going to even out. You're going to stay well under the recommended annual dose. Use of protective garments. Suitable protective garments should be worn by the radiographer whenever it is possible. Okay, this says whenever structural or mobile protective shielding is unavailable, wear your garments anyway. Okay, even if you're standing behind a little lead shield, would you not have an apron on if you're still in the room? Of course you would. Okay, a protective apron should be assigned to each mobile unit. Wear your aprons. As a student, it is required, but when you become a technologist, a lot of people don't do that. You need to be able to do that. You should get in the habit and keep that habit to prevent your scatter radiation dose. Using a mobile X-ray unit, remote control if available, to leave the immediate vicinity and use distance before you take that exposure is your best protection. If you do not have a remote control available, the cord leading from the switch must allow you to be at least 2 meters from the patient, the X-ray tube, and the useful beam. Okay, so stand back as far as possible before you hit that exposure button. Now this looks right here, this is mobile radiography we're talking about. This is where you should stand during mobile radiology procedures, okay? Radiographers should attempt to stand at a right angle to the patient. And if you look at this picture, it's showing you this is the primary beam, okay? And these orange rays are what is coming off the patient in scatter radiation. And right in front of the patient at these angles, around the primary beam, has the most scatter radiation. Off to a wider angle away from the primary beam, scatter radiation, but less than close to the primary beam. Farthest away from the primary beam at a right angle to it, the least amount of scatter radiation. So keep that in mind. I know that's almost impossible because our mobile X-ray unit and the control are back over here, but you do have a cord on your portables or a remote. Try to use distance or get way over here or way over here and be at a 90-degree angle to your patient. Okay, protection during C-arm fluoroscopy. Okay, personnel exposure from scattered radiation during C-arms. You need to exercise a little bit more vigilance than you normally would. The exposure directions are less predictable with using a C-arm. This equipment is frequently operated by physicians whose training and experience in radiation safety do not match your own or the radiologist. The exposure of personnel is caused strictly by scatter radiation from the patient. So the exposure rate is caused by scatter near the entrance surface of the patient. So where the X-ray tube is entering the patient, that exceeds the exposure rate caused by scatter near the exit. So the location of the lower potential scatter dose is on the side of the patient away from the X-ray tube. I'll show you a picture of that. So for instance, the X-ray tube here is on the side of the patient. So say you're doing a shoulder or humerus, okay, or a total, and they want to see a picture and you bring in the C-arm. You put the X-ray tube here. You're going to have the highest level of scatter next to this X-ray tube where it hits the patient. You're going to have the lowest level of scatter next to the image intensifier. Okay. The need for the protective apparel during C-arm procedures. The unit to be energized for long periods of time will increase your radiation exposure. So personnel that are routinely operating a C-arm fluoroscope must wear a lead apron. It needs to be, just like in the fluoro room, 0.5 millimeter lead equivalent. And you need to wear a neck and thyroid sheet, 0.5 millimeter lead equivalent as well. Appropriate monitoring of imaging personnel is mandatory. For increased radiation safety, it is best to place the X-ray tube of the C-arm under the table and the image intensifier over the table. You also need to minimize beam on time. Be aware of the cumulative timer. Use the image storage device, for example, last image hold. Position the image intensifier end of the C-arm closest to the patient. Collimate the X-ray beam to only the anatomy of interest. Use distance whenever possible for yourself. And use the magnification feature very sparingly. It should be used only on the request of the physician. Magnification feature takes more intensity to produce that image. More photons are required hitting the patient. Therefore, more scatter radiation is being produced. Okay, protection during high-level control IR procedures. All of the standard precautions and procedures for the reduction of the dose are applicable also during IR. Even more important here because of the extended length of these procedures that fluoro is on, the large number of digital images that are taken, the frequent use of the high-level control boost mode, and that just shows very, very small structures better. That's why it's necessary in IR. The exposure rate may significantly exceed the rate used in routine fluoro as a result. For instance, if they're using high level or boost mode, you can be exposed to 20 to 40 centigrays per minute, and the maximum allowed in the regular fluoro suite is 10 centigrays per minute. Okay, so you can help in these high fluoro situations in the high level IR suites as the radiographer. You can verify that dose reducing features are available in good working order and you know how they work so that when the radiologist wants to use them, you can utilize them. You can also instruct how they're used on your machine. So the features include high quality low dose fluoro mode, and that can just using less dose still have a good quality image. Pulsed versus continuous, manual collimation, the correct beam filtration, removable grids, road mapping, and that's just a subtraction, time interval differences, and last image hold mode. Protection during these high-level control IR procedures. The biggest protection is decreasing the duration of the procedure and taking fewer digital images. That's not in your control, but that's what the biggest protection is. Okay, other than that, reducing the use of continuous fluoro mode in relation to pulsed, so pulsed is preferred. Keep the protective curtain, if available, present on the image intensifier, or keep a scatter shield in place during the procedure. And this is where you can have one of those overhead barriers available for the radiologist or yourself. Stand behind them as well when you're doing C-arm procedures. And then regularly use the last image hold feature to view that recent image so you don't have to fluoro again to see where they're at. Extremity monitoring, this is a little side note. The hands and forearms of a lot of radiologists and other physicians, especially in the heart cath lab, are getting irradiated a lot. They are subject to large radiation exposures. If the safety protocol is not carefully followed, and that's not always possible for some of these physicians, you need to be aware of the dose limits that the NCRP has established. There is an annual equivalent dose limit to those localized area of the skin and the hands of 500 millisieverts. That's the annual for just the skin and hands. Still remember, though, that the whole body limit for occupationally exposed personnel is 50 millisieverts. Okay, the 500 millisieverts just applies to the skin dose, the localized dose for the skin and the hands. Protective gloves should be worn, therefore, whenever feasible by the physician whose hands will be close to the beam. Okay, now we're going to, lastly, we're almost done. we're going to get into the X-ray suite design, okay, and actually building X-ray suites. And there's a couple things that you need to remember. Okay, so to reduce the equivalent dose to you radiographers and also to the general public, you have to build safe, shielded X-ray rooms that prevent that energy beam from exiting through those walls and doors and windows. And the barrier considerations that they take into mind when they build these rooms and come up with these guidelines are the KVP, which is the mean energy of the X-rays that are going to strike the barrier, if it's going to be a primary or secondary wall, and the workload and the use factor and the occupational factor for that area. Okay, as a result of all of these guidelines and recommendations when you build an X-ray suite, you always err on the side of caution, so you over-shield a room based on what you think the room is going to be utilized at, who's going to be on the other side of the wall, if it's a control area on the other side of the wall, or if it's general public. So all of these things go into consideration, and it is much more affordable to put the lead lining inside these walls under construction than it is to add shielding later. So they over shield when they construct these suites. Okay, the shielding categories that they are shielding for are the primary beam and then the secondary, which is going to be scatter and leakage radiation. Okay, the calculation considerations that they take into mind when they're building an imaging suite are the workload. Workload is designated by a W, and it is the radiation output. It's the time the unit's actually on. So when that X-ray tube is energized, that is the workload, and it is usually designated in units such as milliamperage per minute per week. Okay. Inverse square law, of course, applies. The use factor is also known as the beam direction factor. You need to remember that. That's a test question. And it's the quantity that was introduced to select the contact time that most structures in that suite are going to be struck by radiation. Okay. And then the occupational factor is used to modify the shielding requirement for a particular barrier, either primary or secondary, by taking into account who's going to be in there during that week, during that work week. Okay, and this is just some extra information. I don't think you need to know all of this. Just know what the use factor could be used for. If it's full use, floors of radiation rooms, things like that, you use a use factor of 1. Partial use, you use a use factor of 1/4, and so on and so forth, based on these guidelines of what this wall is used for, or ceiling, or floor, if you have somebody underneath you. Okay, other calculation considerations. You can't really see these numbers very good. I apologize for that. The controlled and uncontrolled areas. There's weekly maximum permitted equivalent doses based on if it's a control area or if it's an uncontrolled area. If it's a controlled area, the weekly maximum permitted equivalent dose, and you need to remember this, is 1 millisievert. Sorry, you can't see that very well. Just write that down, and it is in your textbook. And I believe it is on page, looks like it is on page 293 in your textbook. Yes, right here, 293 to 295. 293 is where these numbers right here are. So the weekly maximum permitted equivalent dose for a control area is 1 millisievert. Okay. For an uncontrolled area, it's 20 microsieverts. So of course we get more absorbed radiation due to the fact that we, as a number of the general population, are a very small number of people. Okay, and you can read more about that in the book. Just remember, for each wall, door, and other barrier in an X-ray room that needs to provide protection against radiation, the product of W, remember what the W is used for? That's called the workload. The U is the use factor, and the T makes no sense, but it's the occupancy factor. All of these things go into determining what the barrier lead equivalent needs to consist of. Okay, so primary barrier calculations utilizes the publication of the NCRP report. They give guidelines to describe what the thickness needs to be consistent of to be sufficient to reduce the air kerma in that occupied area. And there is a ratio involved. The P over T. P refers to the permissible weekly radiation dose in that area. And remember, if it's a controlled area, it's 1 millisievert. If it's an uncontrolled area, 20 microsieverts. Okay. The T is the area's occupancy factor. How many people are going to be in that control area every week? How many people are going to be in that general public area every week? That goes into that primary barrier consideration. Secondary barrier is going to be there to intercept scatter and leakage radiation, and the use factor for secondary barriers are always going to be the number 1. Scatter radiation shielding requirements. The energy of the scatter radiation is equal to the primary radiation. Okay, the intensity of radiation scattered at 90 degrees at a distance of 1 meter from the source is reduced by a factor of 1,000. You need to remember that. That's an important number to remember. Just remember it's 1,000. Leakage radiation penetrates through the X-ray tube housing walls or through the sides of the collimator when the beam is on. Maximum permissible leakage is a rate of 1 meter from the target of the X-ray tube in all directions. It cannot exceed 100 milliroentgens per hour. And that's if the tube is being operated continuously at the maximum kVp and MA. Okay, there's new approaches to shielding and barrier calculations, and they are in the NCRP report number 147. They're very rigorous. They use very finite, minute numbers, and so they're very precise. Okay, this again is a table on those factors. So workload, this is the new approach. Workload, they're using more realistic data. The leakage and the scatter, the explicit barrier calculations, they're down to however many decimal points, not anything that you need to remember for my test. The use factor has been adjusted for beam direction data to reflect actual usage patterns. I'm not sure how they get that data, but there you go. And the occupancy factor has realistic assumptions of occupancy versus just guessing who will be there and how many people in 1 week. Okay, and lastly, we are done. Lastly is X-ray signage. You have all seen these signs, but they are necessary. It is required in an imaging suite. This is part of your radiation protection. Signs must be posted in any room or area where radioactive materials or sources are used. The beam on indicator sign must be on when an exposure is being made. It must be self-illuminating when that equipment is energized. Therefore, if you're paying attention, you should never be walking into an X-ray room when an exposure is being made. Okay, and that is it. Sorry, that was very long-winded, but that is chapter 14, and there is a lot of necessary information that you need to take with you to your boards. So there you have it. Good luck and have a good weekend.